Okay, in this video we're going to try to solve a slightly more difficult problem. And just to remind you, in the previous video we derived, let's say we didn't rely on static friction at all. What speed, or given a speed that you're driving at, what angle does the road need to be banked at so that you don't skid out as you are driving at a given speed. And we found that this was the critical angle theta, that you need to bank the road such that you don't need to rely on friction at all. So basically we completely turned off friction and did this calculation. Now we're going to go ahead and turn on friction. So this example, a car's tire have coefficient of friction µs with the road. Suppose you're given a banking angle theta and radius of curvature r. Find the minimum and maximum speeds that the car can travel without slipping on the road. Okay, now let's go back to these parentheses. They're saying that this theta is greater than arctan of µs, so the car would slide down if the speed is 0. What this is referring to is the following case. Let's just think, forget cars, we can just put a box here, but it can be a car. If you have a car that's on a slope, if you keep making the slope steeper and steeper, at some point the car is going to start slipping to the inside of the road. So this is a static car, by the way. The car is not moving, the car is just parked. So I've shown here the calculation for how big can this angle get at the threshold at which you start slipping. And the condition basically is that your force of static friction that's opposing you from slipping down needs to be at its maximum value. So I went ahead and plugged in mu sub s times Fn. And then the other condition is we basically find that threshold by saying that the acceleration has to be 0 when we're maxed out with static friction. Basically, if this theta became any larger, so the component of gravity along here became any larger, basically we would get a non-zero acceleration after that, because if this grows anymore, Fs max can't grow anymore because it's at its maximum value. Okay, so that's what this angle is talking about. Now let's go back to the situation. What's being said here is the following. So I have two pictures here. Let's first pay attention to this picture, which is saying we're going as fast as we possibly can. When you go as fast as you possibly can on a banked road, on a curve, so let's say this road is coming in like this. So you're driving in, coming in towards the front of the page. Well, if you drive too fast, you're going to skid outward. Okay, that's one case. The other case is, let's say you drive too slow or you're completely stationary. Well, in that case, we know this angle is bigger than the static friction can just support. So movement actually helps keep us on the road in the other extent. So there's the slowest you can drive before you slip inward, and this is the fastest you can drive before you slip outward. That's what this question is asking us about. So now let's go ahead and try to do that calculation. Here I'll walk you through the calculation for the minimum case. So I've gone ahead and copied the free body diagram here. What I'd like you to do actually is pause the video and try to write the sum of the forces in the radial direction and the sum of the forces in the vertical direction, y, and try to figure out what's the minimum speed you can move with and not slip downward. Once you've done that, you should watch the rest of the video. So what we've done here is started with the radial direction. So in the radial direction, we have the radial component of the normal force. So the normal force is in this direction here. The radial direction points this way. So we need to figure out what component of the normal force points in this direction. Well, we know this angle here is theta, and if I were to draw a right triangle using the normal force, I see that this is the opposite side of this right triangle. So this side will be Fn times sine theta. That's my first force in the sum. Then I also have a component of the friction force that is in this direction. So let's go ahead and take a look here. If I extend my radial axis this way, I know that this angle is the complement of theta. So if, let's say, this was 20 degrees, we know this here would be 70 degrees. Knowing that this is the right angle, this is also 20 degrees. So we can go ahead and label the fact that this is also theta. That means the radial component on this right triangle for the static friction is going to be a cosine. So Fs max times cosine theta. Those are the only two forces we have in the radial direction. And then since this thing is moving in a circle, at a constant speed, it has some centripetal acceleration in the radial direction. So we set that equal to m times the centripetal acceleration, which is v squared over r. So I'll go ahead and remind you, this here is essentially m times ac. So we're still saying sum of the forces equals mass times acceleration. The acceleration in this direction just happens to be the centripetal acceleration, which is v squared over r. Okay, so algebraically, this is our x component equation. I've just replaced fs max with mu s times fn cos theta. Should go ahead and add a subscript s to be complete s. Okay, next up, let's work with the vertical direction. So in the vertical direction, we know the normal force is going to have a component this way, and that's going to be the cosine in this right triangle. So fn cos theta, and it's positive because it's upward. Then we have the vertical component of the force of friction, and again, in this right triangle, the sine of the angle, so fs max times sine theta, and it's also pointing upward, so that's positive. And then finally, we have force of gravity downward, so minus mg. Again, we replace fs max with mu sub s times fn. Let's make sure we add the subscript mu sub s. Then we've just done some algebra to factor out a fn from both terms here, factor out a fn from both terms here, and we've got this equation. Now that we have two equations that are both in fn, and we don't know what the normal force is, so there's few ways of solving this set of equations for both fn and this speed, the minimum speed we're looking for. The easiest way to actually solve is to divide the two equations by each other, and when we do that, we get the following expression. And the conditions that we've set here is what is the minimum speed we can drive with to max out this force of static friction, and figure out what's the slowest we can drive. So in this equation here, if we get velocity by itself, you get the following expression. Now what I'm going to leave up to you is to do the calculation for Vmax. So the calculation for Vmax is very similar. The only thing that changes is now force of friction is going to be in this direction, because you're trying to drive as fast as you can before you skid outward.